Okay, Navya, let us begin.
Yeah.
Good morning, sir, and good morning, one and all. Everything happens for a reason, and the reason is physics. I really much agree to the statement as the reason we all have gathered here today itself is physics. We are all familiar with quantum mechanics, which is an important tool to understand at theoretical level electronic structure of chemical compounds and mechanics, thermodynamics, and kinetics of chemical reactions. To understand the various aspects of quantum mechanics and quantum mechanics in Heisenberg picture in particular, we are here to witness the seminar led by respected Dr. S.V.M. Sathyanarayana. First of all, let us invoke the blessings of Almighty. To lead us with prayer song, let me invite Miss Binny B. Vargas.
Lord, I confess, going here, I find my rest. Without you, I fall apart. You're the one that guides my heart. Lord, I need you. Oh, I need you. Every hour I need you. My one defense, my righteousness. Oh God, how I need you. My one defense, my righteousness. Oh God, how I need you.
Thank you, Binny. The world is full of diamonds and gems, and we are having some of them here today to build this event. With this note, I would like to give my heartiest welcome to our Honorable Chief Guest, respected Dr. S.V.M. Sathyanarayana. Dr. S.V.M. Sathyanarayana is an expert in the area of statistical mechanics and quantum information science. He was a former scientific officer in Radiology Safety Division and currently he is an associate professor in the Department of Physics at Pondicherry Central University. With great pleasure, I welcome you, sir. Let us now welcome the woman who doesn't need any introduction and known among all of us for her wisdom and knowledge, our respected principal, Dr. Rita Leda Dikauta. Undoubtedly, we are here fortunate to have a principal who is backbone of our institution. I welcome you, ma'am, with great respect. Now, I would like to welcome our head of the Department of Physics, dear Dr. Roslina Thomas. Welcome you, ma'am, to this auspicious event. Next, I would like to welcome the program coordinators, Dr. Sister Vinci John and Dr. Shidamol GP, and all other faculty members of our department for their wholehearted support and motivation. And I would also like to extend my warm welcome to the HODs, faculty members, research scholars, graduate and postgraduate students from various other colleges. Once again, I welcome you all and let the session unfold the world of knowledge. Now, let me invite Dr. Roslina Thomas to speak a few words.
Good morning, one and all present here. Most respected Sathi sir, dearest principal, uh, Leda ma'am, all the faculty present here, my dear students, and most valued participants. Postgraduate Department of Physics, St. Joseph College for Women, Alappuzha, is very much delighted to host a webinar with Satya sir. I know, sir, through Academy of Physics Teachers, theoretical workshops conducted over 5 years, uh, which most of us are familiar. Maybe most of the teachers present here are familiar with. It covered mathematical physics, classical mechanics, quantum mechanics, thermodynamics, and statistical physics. And it was conducted for physics teachers across Kerala. And Satya sir was the resource person to 90% of those workshops. Once you start attending sir's classes, you become addicted to it. So am I. The series came to an end just because of the pandemic, and we teachers really miss sir's classes a lot. As all teachers are familiar with, Satya sir is very simple and down-to-earth person. I'm always admired by the way he teaches each topic according to the audience. Sundays mean rest days for all of us. It's a time to spend with family and friends and laze around, doing not much. For Satya sir, Sundays mean coming to Chennai to help students and helping them to pass exams like CSIR, JRF, and NET and become science researchers and faculty. He has been doing this for free every Sunday for more than 25 years without a break. Today, hundreds of researchers and faculty across India are thankful to him. Some of them in turn pinch him to keep his class going if Satya sir is away. Many of his students are today at frontline research institutions. Dear all, today we are blessed with such an eminent personality, and I take this opportunity to thank Satya sir personally for sharing his valuable time and interacting with our students. I would like to wish all the participants a great learning time ahead. Thank you.
Thank you, Ms. Roslina, Ms. for your valuable words. Now, let me invite Ms. Neha Kimaria to deliver a few words about our resource person, respected Dr. SVM Sathyanarayana.
Good morning, one and all. I am profusely overjoyed to take this opportunity to introduce our chief guest of the day, Dr. SVM Sathyanarayana. Professor Sathyanarayana is the Associate Professor in the Department of Physics at Pondicherry Central University. He has completed his PhD in the year 1998 from the University of Madras. He had been working as the scientific officer in Radiological Safety Division, Indira Gandhi Center for Atomic Research, and later on, he joined as a faculty in the Department of Physics, Pondicherry Central University. He is an expert in the areas of statistical mechanics and quantum information science. He has guided more than 30 master students, 9 MPhil students, and a PhD student. He has published more than 20 research articles in reputed journals and a quite number of articles in conference proceedings with 152 citations. Sir is one of the national level coordinators of Physics Training and Talent Search Program, PTTS, which is a national level program to provide a platform for motivated students to interact with peers and experts in the field through active learning methodology. I would like to thank our dear Head of the Department of Physics, Dr. Roslina Thomas, for inviting Sir for this session, and I'm fortunate to listen to his lectures as a postgraduate student. Dear participants, we are much privileged to have such an eminent personality like Dr. SVM Sathyanarayana, who is going to ignite us with his knowledge in quantum mechanics in Heisenberg picture. On behalf of all teachers and students of Postgraduate Department of Physics, St. Joseph's College for Women, Alappuzha, Kerala, I wholeheartedly welcome you, sir. We are really honored with your esteemed presence. Once again, thank you very much, sir, for your valuable time, and I wish the very best to all dear participants. Thank you.
Thank you, Sneha. We feel honored to have with us our Honorable Chief Guest, Dr. SPM Sathyanarayana, and I feel privileged to invite him to begin this session. So please.
Hello, good morning. Am I audible to all of you?
Yes, sir. Yes.
Okay. Okay. So at the outset, let me thank Dr. Rosalina for inviting me to give this lecture, and also thank her for the kind words that she has told about me. Also thank Sneha and Navya for their kind words about my work and whatever small profile that I have. So today we are going to discuss Heisenberg picture, quantum mechanics in Heisenberg picture. But before I begin my lecture, I want to just ask some stray questions here and there. So, is this a part of your MSc syllabus? I think yours is a postgraduate department.
Yes, sir.
Okay. So, what is there in the syllabus? Can any of you remember? Only one line is there, Heisenberg picture.
No, sir. Actually, they have matrix representation of wave function operators, then Schrodinger equation,
Okay.
also unitary transformations.
Okay. Okay. So, so let me start somewhere. So what I want to tell you is that this lecture can be made more useful if you in between interact and then give me some feedback, then we can make this more useful. Okay, so please feel free to stop me, and I will be happy to clarify points there and then. Okay, so I think, can you see my screen?
Yes, sir.
So what are you reading the title?
Quantum mechanics in Heisenberg picture.
Okay, okay, very nice. Okay, so what I will do is we will have to, of course, talk about quantum mechanics that we have been doing. So it is something to do with time evolution, right? So in quantum mechanics, we always start with Schrodinger equation, right? So let's say that we have a system. Okay, so the system could be a single particle. Okay, single particle. Of course, this particle has what we say a dual nature. That means it has both wave nature as well as a particle nature. then the state of this particle is in general represented by some kind of a symbol like this, and this is called a ket. Okay, and this is generally an element of a vector space. Okay, so please note down certain technical words if you don't understand, and then you can ask them. So it's an element of vector space, and technically this vector space is called a Hilbert space. Okay, so if you don't understand Hilbert space, just think that as a vector space. That's sufficient for our purpose now. And dynamics. So what is dynamics? Given psi at time t is equal to 0, so this is what you call as initial state. Okay, we can solve I h cross del psi del t is equal to h psi. To get psi at time for all. And this equation is what is called Schrodinger equation. Okay, and any property, a property which is also called an observable, a property called an observable is a self-adjoint operator. This is what we call as Hermitian. Okay. Now, in a state psi of t at time t, the property A is given by the expectation value of Hermitian operator A. Denoted by this angular bracket like this at time t. Now, how do you define this? You define this as A expectation value at time t is equal to psi of t A and psi of t. This is called the expectation value. Okay. Now there are certain interesting things that you should know, or you already know, that if you measure A, A of the system when it is in state psi of t at time t, the result belongs to the set of eigenvalues. Eigenvalue of this operator A. Okay. That means if phi n are eigenstates, of A with eigenvalues, let's say an, that means you have an eigenvalue equation like this. A operator acting on phi n will be an phi n. Okay, if these are eigenvalues of A, then result belongs to this set of an. That is what I wrote up. But it turns out that this result, we don't know beforehand what is going to be the result. It randomly will be one of the eigenvalues. So one can ask a question: the probability to get some am as result is given by result at time t is given by, so let me call it as Pm of t, that is given by pi m psi of t modulus square. We get this because the eigenstates of A, okay, so these eigenstates of A, phi n, form a basis of the vector space. And psi of t belongs to this vector space. And any vector that belongs to vector space can be written as a linear combination of this. Psi of t can be written as some Cn into phi n. Okay, so since this is not only a basis, it is called an orthonormal basis. That means in order to get Cm, you multiply this with phi m, psi of t, to get Cn pi m pi f. So that will be equal to sum over n, this sum over n Cn, this will be delta Nn. That means this is equal to 1 only if n is equal to n. So that is how I get this. So this is in general a complex number. So modulus square of that will give me the probability. So this is what gives you the probability to find what is the probability of getting that. Okay. Now one last piece of information that gives us the state after the measurement. Suppose if A is measured and an answer AL is obtained. That means this is obtained as the result. Then the state of the system, or this is called post-measurement state, is given by pi n. Whatever is the eigenstate corresponding to this eigenvalue will be the state. This is called collapse of a state, or state reduction, or quantum jump. These are different names with which this is referred to. But anyway, the meaning is that whatever was the initial state, the state after measurement is that eigenstate whose eigenvalue is obtained as the result of the measurement. Okay, so this is in some sense the summary of all the postulates that you have in quantum mechanics. Okay, so any questions at this point? So this is something which you all have probably known if you have done quantum mechanics 1 course. These are something that you would study right in the first month of the course. So that is why I try to do this a little fast. So if there are any questions, you can ask me. Otherwise, you can ask me as and when you get the questions. So I would say that this particular module is my first module. We'll call this as some postulates. Now let me talk about my second module. This is typically about time evolution. Now we have Schrodinger equation. So time evolution, we have made a statement given the state at time t equal to 0. We can solve the Schrodinger equation, IH cross L psi by del t is equal to H psi. What is this H? This is called the Hamiltonian to get psi f. So here H is the Hamiltonian operator. Okay, here H is the Hamiltonian operator. Okay, now here I'm going to make an important assumption. Assume that H does not depend on time. Okay, but this is an important assumption, and we will try to see what happens if we relax this assumption later. But for the time being, let's assume, because most of the problems that you have done in your quantum mechanics course are like this, except when you do time-dependent perturbation theory. So since this covers a large body of your quantum mechanics syllabus, let me assume this, and then I will make some remarks if we relax this, what happens towards the end. So if H does not depend on time, then we can formally solve this Schrodinger equation. We can formally solve Schrodinger equation. That is, forget about the fact that this H is an operator and just solve this like a first order differential equation. And if you do that, you will get psi of t is equal to e to the power minus I by h cross t h acting on psi of 0. Now, since h is an operator, this is all e to the minus I by h cross t h is also an operator. Okay, so let me call this operator u of t. Why I am calling it as u of t? If h is Hermitian, u is unitary. Okay. So since h dagger, the adjoint of h is h itself, we have this u dagger u is equal to u dagger. That's equal to identity, which means u dagger is u's inverse. So u of t is a unitary operator. Now, if you see, state at 0 time is becoming state at time t by a unitary transformation. Okay. So psi at 0 goes to psi at t by the application of a unitary operator. Okay, that is unitary operator. So because of this, we say time evolution of a state in quantum mechanics is unitary. Okay, so unitary evolution, that is what we always read in the books, right? It's a unitary evolution. Okay, so we now know that this time evolution is like this. Now we will talk about this operator's action on this state. Okay, so in this particular case, we will ask a question: how to implement this time evolution? So in this, let us talk about two cases. Case 1, the initial state psi of 0 is a stationary state. Okay, you must have heard this name stationary state first when Bohr gave his stationary orbits, right? But basically, what is a stationary state? Stationary state is an eigenstate of Hamiltonian. That means stationary state is by definition an eigenstate of Hamiltonian operator. So let us say that when H acts on this psi 0, let's say we get E psi 0. If it is an eigenstate, there will be an eigenvalue associated with that. Okay, so let us say this one. Then, what about h square acting on that? Acting on psi of 0? Is it an eigenstate of h square? Yes, it's an eigenstate of h square, but the eigenvalue is e square. Right? Now I continue this logic and I say any function of h, this psi 0 is an eigenstate of any function of h. It could be h square or h cube or e power h or log h, whatever it is. And what should be the eigenvalue? Simply f of t. For every well-behaved function, we will have this correspondence. Now what does that mean? If psi of 0 is an eigenstate of h, then what will be psi of t? We have psi of t is equal to e power minus I by h cross into th acting on psi of 0. So you can say that this unitary operator is like a function of h, right? So what will that be equal to? That is equal to, wherever h is there, I have to put e. So e power minus I by h cross e into t into psi of 0. What does that mean? Psi of t is differing from psi of 0 only by a phase factor. A phase is getting multiplied. That's the time evolution. So we know if it is a stationary state, time evolution is very trivial. Okay, so this is the case 1. Now case 2 is slightly complicated. Now psi of 0 is a non-stationary state. Non-stationary state. Now if psi of 0 is a non-stationary state, that means it is not an eigenstate of Hamiltonian, but we can, so we are interested in finding what is psi of t. Okay, but then we cannot use the above logic because f of h of psi 0 is itself not e of psi 0. So f of h of psi 0 will definitely not be equal to f of e of psi 0. So we have to use another trick. Okay. Now what we know is that every Hermitian operator, however, h has its eigenstates. Which can be found out. Okay, how do you find that out? By solving h phi n is equal to en phi n. So this is what you call a time-independent Schrodinger equation. In some books, we call this as people call this as time-independent Schrodinger equation or eigenvalue equation. So if you see most of the problems in your syllabus, you would have solved this equation. Whether it is particle in a box or harmonic oscillator or rigid rotator or particle on a ring or hydrogen atom, helium atom, whatever problem that you have solved, you are always trying to solve this. Now, why is this equation so important? Why we are always solving this? The reason is, if you know stationary states, that means these are stationary states, right? Phi n, these are stationary states. Stationary states. And they form an orthonormal basis. Just like in the previous case, orthonormal basis of the state space. State space is the Hilbert space or the vector space, whatever. Because of that, what we can say is that So let us call this state space with some curly H symbol like this. Okay. Now my psi of 0, the initial state, which is a non-stationary state, that belongs to this state anyway, which implies this psi of 0 admits an expansion in terms of this basis, sum over n, Cn, phi n. I can have this. This is something which is admissible. Now what I will do, so to find psi of t, okay, I use the above expansion. Psi of t is equal to, so e to the power minus I by h cross t h, acting on psi of 0, but psi of 0 is this one now. So Cn phi n. Now this is a linear operator, so it can be taken inside. So that is equal to sum over n Cn e to the minus I by h cross t h acting on phi n. So you can see, but what is phi n? Phi n is a stationary state. So when e power minus I by t h cross h acting on phi n, what I will get? Wherever h is there, I will get En. So that is equal to sum over n Cn e power minus I by h cross En into t phi. So this is your time evolution. So you can see, even if you have a non-stationary state, the time evolution of the state can be figured out if you know stationary state. That means the whole time evolution of any state can be obtained if you know stationary states. Then you have to simply expand the given state given the initial state in terms of the stationary states, and then you can find out what is the time evolution. So this is the time evolution of the whole class of states. If they are stationary states, it is simple. If they are non-stationary states, then you have to expand that initial state in terms of the stationary states, and then it's a linear combination of time dependence of the stationary states. Each stationary state will have a time dependence like this, and then you can expand that. Okay, so this is as far as the time evolution is concerned. Okay, any questions at this point? Or any feedback? Am I going fast, slow? Are you all following?
Yes, sir.
So should I go slow or fast? Or is this too elementary?
This is perfect, sir.
Perfect. Okay. Okay. So this is something that we have. So let me just illustrate this. Okay. So let me just illustrate. Okay. So we know that I'm not going to solve this problem, but we know that we have some one-dimensional harmonic oscillator. So we have a Hamiltonian, which is given by p square by 2m plus half m omega square x square. Okay. And you can talk about you can also write this matrix in terms of some number operator as A dagger A plus half. Okay, so this equation can be written in this fashion. By probably you write down your A as square root of m omega by 2h bar into x operator plus IP operator divided by square root of 2m h bar. So you write it like this, and A dagger is with a minus sign. Okay, so A dagger is equal to this one minus this one. So like that, if you define, you can write like this. Then there are some number eigenstates which are called n, and h acting on that, you will have n plus half into h cross omega into n. So this harmonic oscillator, you might have solved it. So I am just, and n will be starting from 0, 1, 2, etc. It will go on. So that means this harmonic oscillator has got energy levels. So this is ground state corresponding to n equal to 0. And this has got an energy E0 that is equal to h cross omega by 2. And then you have first excited state, which is called 1. It has E1 is equal to 3 by 2 h cross omega, and so on. Okay, so the energy difference, E1 minus E0 is h cross omega, E2 minus, so any En plus 1 minus En is equal to h cross omega. So equally spaced energy levels. That is what we have for this one. Now, supposing, so let us say that, so let psi of 0 be equal to 1 by root 2 times ground state plus excited state. So this is the initial state. Be the initial state. Okay. Now you ask a question, what is the state? What is the state at time t? Okay, so how do you do this? So psi of 0, so that means your psi of t is equal to e to the minus I by h cross t Hamiltonian acting on psi of 0. But then this psi of 0 is what? Is equal to e to the minus I by h cross t h acting on 1 by root 2 0 plus 1. That is my psi of 0. So that is equal to 1 by root 2 into e to the minus I by h cross t h acting on 0 plus e to the minus I by h cross. This is a linear operator, so it can go act on each one of that state separately, acting on 1. But 0 and 1 are stationary states. So what will I get? I will get 1 by root 2 e to the minus I by h cross t. Ground state energy is h cross omega by 2. 0 plus e to the minus I by h cross t. First excited state is 3h cross omega by 2. Correct? So that is into 1. That is what the time evolution is. Okay, you cancel this h cross here. So you have 1 by root 2 into e to the power minus I omega t by 2 plus e to the minus I 3 omega t by 2. So that is the state at a later time. Now, interesting results can be obtained if you ask a question. So let's say, let x be the position operator. X be the position operator. So we ask a question, what is the expectation value of x at time t? What is the expectation value of x at time t? So that's the question that we can ask. Now, how do you do that? By definition, the expectation value of x at time t is equal to state at time t into position operator and state at time t, right? This is the expectation value that we have defined. If you go back to postulates section, so we said this is how the expectation value is defined. So here for a, and now we are asking for x. Okay, so this is something which we know. What is psi of t is something that we know already. And what is x? Now go back to this definitions. I know a and a dagger. From here, you can write down x as square root of h bar by 2m omega into a plus a dagger. Okay, not only that, that means you have to add these two things. So the p term will cancel. So you know how to get x from this. And also note the following, or recall, that this action of a on the state n is root n into n minus 1. And similarly, action of a dagger on n is equal to root n plus 1 n plus 1. That means this will lower the index, this will raise the index. Okay, that is why these are called lowering and raising operators. So now I can use all these things and then write this as, so there will be a 1 by root 2 from here and 1 by root 2 coming from here, that is 1 by 2. And this psi of t bra vector will be a complex conjugate of that. That means e power I omega t by 2 into bra vector 0 plus e to the power I 3 omega t by 2 into bra vector 1. And then we have this x operator. X operator is square root of h bar by 2m omega into a plus a dagger. And then we have e power minus I omega t by 2, 0, plus e power minus I omega minus 3 I omega t by 2, 1. Okay, so now you can see, so when a is acting on 0, there is no lowering possible, so that will be 0. When a dagger is acting on 0, that will become 1. But a dagger is acting on 1, that will become 0. Okay, so you can see that there are 4 terms here, right? In fact, there are 8 terms. 0a0, that will be 0. 0a1, that will be non-zero, correct? That is 0a0, that will be 0. 0a1, that will be non-zero. So let me write that first. So that is equal to half I plus I omega t minus 3 omega. So it will be basically e power minus I omega t 0 a 1. That is one term. And 0 a dagger 0. That will not contribute because a dagger on 0 becomes 1 and 1 with 0 will be 0. So that is not going to contribute. And 0 a dagger 1 is also not going to contribute because a dagger on 1 becomes 2. So 0 2 will not contribute. So the only other term that will contribute is this 1 a dagger 0. So that is plus e to the power I omega t into 1 a dagger 0. This term contributes. Of course, I have to keep this square root of h bar by 2m omega outside. Now, what is a dagger on 1? Is simply 0. So 0, 0 is equal to 1. And a dagger on 0 is simply 1. So 1, 1 is equal to 1. So this is equal to 1. So what is it that we are getting? We are getting square root of h bar by 2m omega into e power minus I omega t plus e to the I omega t by 2. So what is that? That is equal to square root of h bar by 2m omega into cos omega t. So what is it that we are getting? This is the expectation value of t. Okay, so the expectation value of t is somewhat close to what we observe in a classical harmonic oscillator. Okay, so x goes like cos omega t. But this is specific to the initial state that we have taken. What is the initial state that we have taken? Initial state that we have taken is 1 by root 2 ground state plus first excitation. This is the initial state. So if I take this initial state, then the expectation value of x is given by this. Okay, so this is just an illustration of the time evolution that we have talked about. Okay, so now let me go to my third module. So whatever I have discussed so far, okay, so far quantum mechanics is done in what is called a Schrödinger picture. To appreciate a different picture, we should know what we are doing generally, right? So this is called Schrödinger picture. And what is the speciality of Schrödinger picture, or what is it that we have observed? So here, state evolves in time. According to Schrödinger equation. And operators do not evolve. As you can see, to find out x of t, what I have done, I have only taken time dependent state here and here, but x is something which does not have any time dependence. X is x. So operators do not evolve in time. Okay. But expectation values, okay, expectation values, so time evolution is unitary. Okay, so this is what we have observed. Now let us look at, so one of the questions that is of concern is that in the previous illustration problem, so here we observed that the expectation value of x is similar to classical trajectory, that is x of t. So we make this observation. So one issue is, of course, the formulation of quantum mechanics in terms of the postulates that I have written looks like it's very different from what we know in classical mechanics. Okay, so in classical mechanics we have Newton's equations or Hamilton's equations or Euler-Lagrange equations. So those equations will give us trajectories, and observables are basically position, momentum, angular momentum. All these things are basically functions of position and momentum, and we don't have any wave function here, but the state, the central central quantity here is the wave function or the state, quantum state, which is some vector in some Hilbert space. So there seems to be some kind of a some link is missing. So this is something different, like that we have a feeling. Now let me start with the expectation value. Okay, so expectation value of an observable A is given by, in state psi of t at time t, is given by, I'm going to rewrite that expression here, A of t is equal to psi of t A and then psi of t. Okay. Now using the fact that psi of t can be written as e power minus I by h cross E h acting on psi of 0, we get for this A of t it is equal to psi of 0 into e to the power, I have to write plus because it is a dagger, eh into a into e to the power minus I by h cross th into psi of 0. Correct? I could have written like this, because psi of t is related to psi of 0 by this unitary transformation. Now I can visualize this in the following fashion. So let's say I have psi of 0, that means state is not evolving, but then there is an operator which I will call it as ah of t and then psi of 0. Because the time dependence I could have transferred to this operator, right? So that is, it is just like the way you are looking at it. Instead of time dependence coming from the state, you could have actually said that time dependence is coming from the observable. So AH of t. Now why I am calling this AH of t, where AH of t is equal to e power I by h cross th into a into e to the minus I by h cross th. And earlier, you remember you called this as u, right? So this can be written as u dagger a, u dagger of t, a into u of t. So now AH of t is a unitary transformation. An operator gets unitarily transformed in this fashion. So a unitary transformation of A with unitary operator u of t that is equal to e power minus I by h cross t into h. So this is a unitary transformation. So this operator, this AH of t, is the operator A in the Heisenberg picture. So Heisenberg picture operator. In Heisenberg picture, operators depend on time and state vectors don't depend on time. Just like it is the reverse of what we have seen in Schrodinger picture. In Schrodinger picture, state vectors depend on time and operators don't depend on time. So now what we have to do, we have to give an evolution equation. Okay, so we ask a question, what is the evolution equation? Just like in Schrodinger picture, the evolution what is the evolution equation for AH of t? Okay. Now to understand that, let us try to ask what is dAh by dt. dAh by dt is equal to d by dt of e to the minus I by h cross, plus th a e to the I by h cross t. So that is equal to, first I will write this as e to the power I by h cross th into I by h cross t, I by h cross t, as a t is not there, into h into a into e to the power I by h cross th. That is differentiating the first term and keeping the rest same, plus this side it is minus, plus e power I by h cross th. I will keep this as it is, a into minus I by h cross h into e power minus I by h cross t. So I am a little bit sloppy. Here I have written this after this, here I have written this before that, but it doesn't matter because h will commute with e power minus I by h cross th, so I can flip that if required. So that is equal to, so I could have pulled out minus I by h cross into, so you can see that I can flip this in this fashion, and I can flip this around, no problem, because H commutes with this operator. And I can also flip this around. Then what happens is I have A H into H minus H into AH. Okay, so this minus I can take this to the denominator. I get IH cross. And this is what is the commutator of AH with H. Okay, so what is the evolution equation? The evolution equation simply gives you, take this IH cross here into dAH by dt is equal to AH comma H. Okay, so this is the evolution equation, and this equation is called Heisenberg equation. So the operator which depends on time will actually depend on the commutator of AH with H. So using this, you will find out AH as a function of time. And when you find out AH as a function of time, then you can find out the expectation values. Anything, everything that you can do in quantum mechanics, you can do with this. So this is called Heisenberg picture. Heisenberg picture. So in Heisenberg picture, state is time independent. And operators depend on time. Operators depend on time. Now, operators evolve. Operators evolve according to Heisenberg equation. Heisenberg equation is given by this. Now, one can ask the following question. So, some questions. So, we know now this is the Heisenberg equation. So, let us ask some questions and try to answer. First question. What is the use? Already we are doing quantum mechanics in Schrodinger picture. Why should we use this? Or what is the use of this? Or should we do quantum mechanics in this picture and that picture? So there is no, it is not that this is just another picture. That means it is another formulation, right? Now, what is the use for some problems? For some problems, it is easy and well suited. So if you are doing it in this picture, then you will get the things done very easily. So let me just give you an example to illustrate this. Okay, so you know that this problem is something which you might have done earlier, and if you have not done it, I recommend you do this. So for a free particle, consider initial wave function psi of x comma 0 as some Gaussian, okay, some constant a into e to the minus x square by 2a square. Assume this kind of a Gaussian. You can find this a by normalizing it. Okay, so Gaussian. So here the width of the Gaussian, width is a. That means if we are thinking in terms of a Gaussian wave packet like this, so this is your psi of x comma 0 and this is x. So this width is basically a. Okay, so now you ask a question. Remember, this is a free particle. Now you ask a question. What is psi of x comma t? Okay, and so usually this is called some sigma, right? So sigma of 0 is equal to a. Now, if you have done this problem, you will know already, or you refer any textbook like Schiff or Griffiths or any book where it would have either been worked out or it would have been given as a problem, so you can work it out. Psi of xt is also a Gaussian. Is also a Gaussian. Psi of xt is also a Gaussian. But then you ask, what is sigma of t? Sigma of t actually increases with t. That means if you are talking about a Gaussian wave packet after some time t, so it could be a Gaussian wave packet like this. That means this width is very large compared to that. Okay, so this problem is something which you might have done. If you have not done it, you please do this. Okay, so the Gaussian wave packet, so wave packet spreads with time. So this is what you can observe. Of course, you have to do some Fourier transform and all that in this case. So, but this exercise is something which you can do. Now, the same problem I can visualize in Heisenberg picture in a simpler way. If you have done this problem earlier, so you know how much work is involved. Okay. Now, in Heisenberg picture, I'm going to argue that this is something which can be seen easily. So, in Heisenberg picture, the Hamiltonian is given by p square by 2m for the free particle. Now, let's say I want to ask what is. So now x and p are like operators. X and p are operators and they evolve in time. So let's ask this question. IH cross dp by dt that is equal to the operator P with the Hamiltonian. But operator P with the Hamiltonian is 0 because P commutes with P square. So that implies what? That implies your operator P of T is same as the operator P of 0. There is no evolution in this operator. Correct? Now let us look at x. So IH cross dx by dt is equal to the commutator of x with p square by 2. So that is equal to 1 by 2m into x p square. Okay, so that you can write it as 1 by 2m into 2 times x comma p into p. But x comma p is what? This 2 will cancel. X comma p is IH cross. So this is IH cross p by m. But there is an IH cross on the left hand side, so that will cancel. So we have dx by dt is equal to p by m. So if you solve this equation, then you get x at time t is equal to x at time 0 plus p at time t, but p at time t is same as p at time 0 because of this. We have already seen p commutes with the Hamiltonian, so p at time t is same as p at time 0. So let me write that into t. So this is your solution of the Heisenberg equation, right? Now notice one interesting thing here, that we know that x at 0 time and p at 0 time do not commute. The commutator is given by IH cross. Now I am asking a question. These are operators, right? X and p operators. Do x at 0 and x at t commute? So let us ask that question. So what is x at 0, comma x at t commutator? So that is equal to x at 0 and x at t we already know. That is x0 plus p0 by m t. What is that equal to? x0 will commute, but x0 p0 does not commute. That means 1 over m or t over m into x0 comma p0. But x0 p0 commutator is not 0, and that is IH cross, right? So that is equal to IH cross t by m. So what is it that we are observing? The position at 0 time and the position at time t, position at 0 time and position at time t do not commute. What does that mean? This has some information, right? So let's see what is that information is going to be useful for. Now we have in general if any two operators A and B, let's say, do not commute, and if A, B is equal to some resultant operator C, then we have an uncertainty delta A into delta B is greater than or equal to half of modulus of expectation value of C. Okay, so this is a general result of uncertainty relation. So I am sure you might have seen this or derived it yourself. So what does that mean? So if I apply it to this one, I have delta x t into delta x at 0. Okay, delta xt and delta x0 should be greater than or equal to h cross t by 2m. That is what I should get, right? What does that mean? So this is an uncertainty in, so if you take a Gaussian, uncertainty is basically the standard deviation or the square root of the variance, right? So that means if you assume that there is some uncertainty at time, that is some constant value is there, then delta x t is actually related to, it is increasing linearly with t. So if you actually do that calculation, you will see that this is the factor by which the uncertainty increases or the variance increases. So that result we could get in a very simple fashion by simply looking at the commutation of this. Okay, so you will get the simplicity only when you actually solve this problem yourself. Okay, so I recommend that you should definitely give a try and solve this problem in order to appreciate the usefulness of Heisenberg picture. Okay, so let me give another illustration. Okay, so let us look at second example. Okay, second example. Hello, any question?
I think Lubina has some questions.
Yes.
Lubina Sherin.
I couldn't hear. What did you say? You want me to give some break and ask for any questions? Shall I continue?
Yes, sir.
Okay, so second example is the problem that we have just solved. So if you go back and then look at that harmonic oscillator problem, I started with an initial state of 0 plus 1 by root 2, and then we have seen that the expectation value of x is cos omega t, right? So let us see how to see that here. So here we are talking about a 1D harmonic oscillator. So the Hamiltonian is given by h cross omega into a dagger a plus half, and x in terms of a dagger a is h bar by 2m omega into a plus a dagger. Okay. Now what is important is that here a and a dagger evolve in time in Heisenberg picture. So let us ask what is IH cross dA by dt. That is equal to A with H, the commutator of A with H. So commutator of A with H is simply H bar omega A with A dagger A. Correct? So that is equal to H bar omega A dagger A plus A dagger A. A is 0. So we will have A dagger is, what is commutator A dagger? 1. Right? So this is, so we are going to have H bar omega A. And you can cancel this H bar. Okay. So you get dA by dt is equal to minus I omega into A. So this equation is easy to solve. I get A of t is equal to A at 0 into e power minus I omega t. Okay. Then you ask what is IH cross B A dagger by dt. That is equal to A dagger comma the H, the commutator. And you can see that this will be equal to minus H bar omega into A dagger. Okay. So that gives you A dagger of t is equal to A dagger of 0 into e power I omega t. Correct? So now we have solved this time dependence of these operators. Okay. Now, suppose if you want to ask what is x of t. X of t is equal to A of t plus A dagger of t into square root of h bar by 2m omega. That is my x of t. Now if I want to find out what is the expectation value of this, that is expectation value of x of t in the state zero plus 1 by root. The state doesn't depend on time in this picture. So that means what? I am going to write, that is your expectation value of x at t is equal to 1 by 2, 0 plus 1 into, I have root h bar by 2m omega into A of 0 into e power minus I omega t plus A dagger of 0 into e power I omega t 0 plus 1. Okay, so now you can see that this 0 with this A of 0 and this 1, that one combination will become non-zero. And 0, A, 1 is actually 1. So that means you have root h bar by 2m omega into half e power minus I omega t 0 A of 0 1. Then this 1, this A dagger, and then this 0. That is another term that will be non-zero. That is e power I omega t 1, A dagger of 0, 0. All other terms will become 0. So that you will get square root of h bar by 2m omega. So this is 1 and this is 1. So you have cos omega. So you can see that result is obtained in a more simpler fashion than the previous result. Okay. And you can see that so whatever we have done here, same result we have got here, but now the state is something which we did not evolve in time. We simply put that as 0 plus 1, 0 plus 1 on either side, but it is this operator that has time dependence here, and we get the same result. Okay, so these are the two illustrations that I wanted to give you to say that what is the use. Sometimes in some problems this can become so for some problems, as I said, it is easy and it is well suited. Now let me tell you that in most of the non-relativistic quantum mechanics, that is what we study in our MSc syllabus, Heisenberg mechanics, Heisenberg's method or Heisenberg picture is not used because the Hamiltonians or the system Hamiltonians that we choose are more or less simple. But when you go to relativistic quantum mechanics and quantum field theory, etc., Heisenberg's picture becomes more convenient for developing time evolution than Schrodinger picture. Okay, so Heisenberg picture is, for example, in second quantized notation, etc., when you have so many A dagger, this kind of operators, then this becomes more useful. Okay, it's easy to study such things. Okay, so that is one question. Now the second question that I wanted to ask is, so what is the difference? For example, suppose in the initial case we have written that eigenvalues of A are operator A are measurement results. If observable A is measured. Observable A is measured. Now, are eigenvalues are they same for AH of T? Okay, so this is the question. Now the answer, what do you think the answer is? If they are not same, then I think we are in great trouble, because just because you are trying to do quantum mechanics in some other picture, the physics should not change, right? Your measurement results should not change. Okay, so they have to be same. Yes, they are same. Now, in matrix also, you know that if you have a matrix M, let's say you have a matrix M, and then let's say you do a similarity transformation, SMS, then you become some other matrix, let's say P. Okay. Now, the similarity transformation does not change the eigenvalues, right? So, eigenvalues of M and P are same. This is something which we know in matrices. Now, same thing is true here also, because AH and A are unitary transformed, right? So, AH of T is equal to U dagger A, U dagger of T, A, and U of T. So, the eigen unitary transformation is similarity transformation because U dagger is U inverse, right? So, unitary transformation will not change the eigenvalues. So, eigenvalues of A and AH of T are same for all T. So there is no problem with the measurement results. Okay. Now what can we say about eigenvectors? What about their eigenvectors? They are not same. Let's again go back to our matrix. Let's say M is a matrix and S inverse MS, let's say this is a diagonal matrix. Okay, so this is, let's say, is diagonal matrix. Eigenvalues are same, but for a diagonal matrix, what are the eigenvectors? Suppose, let's say you have a diagonal matrix like this, lambda 1, 0, 0, 0, lambda 2, 0, 0, 0, lambda 3. So what are the eigenvectors of this matrix? Let's say 1, 0, 0 is one eigenvector, 0, 1, 0 is another eigenvector, and 0, 0, 1. For all diagonal matrices, these are the eigenvectors. Correct? Whereas eigenvectors of M are not the same. They are not there. So eigenvectors of M are not these vectors. So therefore, if you have a similarity transformation, even in matrices we know that the eigenvalues will be same, but the eigenvectors are not same. In the same way, when you have eigenvectors of A and eigenvectors of AH are not same. Okay, so eigenvectors of A need not of A. Okay, so now let's ask a question. What does that mean? So there is a general principle which states that, suppose, let's say that you have okay, so let's say I have, okay, so let me put it this way. So I have a state psi, and then I have an operator A, state psi and operator A. Now this state psi, now if you choose a basis, choose a particular basis, choose a particular basis. So let me call it as some phi n. Then both psi and a can be expressed as a vector with components and a matrix. With elements. Okay, respectively. Okay, now what does that mean? That means that your psi of psi can be written as sum over n Cn phi n. Now the Cn are what are called components. Components of psi in the basis phi n. Okay, and your A Mn can be written as phi n phi m A phi n. This is called matrix element. Matrix element of A in the basis phi n. So if you are choosing a basis, an operator can be realized as a matrix. And so this operator A in principle can be written in the following fashion. So I have a phi 1 A phi 1, phi 1 A phi 2, and so on. Phi 2 A phi 1, phi 2 A phi 2, and so on, so on, so on, so on. In general, this may be an infinite by infinite matrix, but one can write this as a matrix. So any mth row, nth column element will be phi m A phi n. This is called matrix element. In the same way, a wave function can be written as a set of numbers. These are like components. This is something familiar in vectors. Like if you have a vector v, we say vx I, vy j, vz, vz k in three-dimensional space, right? Similarly, in an infinite dimensional space, you can write down the operators in the form of a matrix representation like this if you have chosen a basis. Now you know basis is not unique, right? For a given vector space, you can have infinitely many bases. Suppose if somebody chooses, if we choose a different basis, we choose a different basis. Say, I will call this as some phi n prime. Then what happens? Your psi can also be written in terms of this psi. Psi can also be written as sum over n Cn prime phi n prime. Where these coefficients will be different, these components will be different. And similarly, Amn will be Amn prime. That is equal to phi m prime A phi n. Okay, so you will have a matrix with a different components, correct? Different components. The components or the elements of that matrix will not be same as the element of the previous matrix because the basis is different now. But now the question is, now if you have this, now notice this is phi n prime, okay? So now the question is something like this. One of these basis elements can also be written in terms of the old basis. Correct? It is possible to write phi n prime in terms of the old basis. Okay, so every element of new basis, say phi m prime, can be expressed in old basis. What does that mean? That means your phi m prime can be written as some, let's say, alpha m n into phi n. I'm writing this two indices alpha m n because it depends on this m also, it depends on this n also. So this is possible, right? We can write it like this. Right? So you can see that you can get this alpha mn. We can get alpha mn by taking a projection of phi n with phi m prime. Correct? If you take projection of phi n with phi m prime, I will get alpha mn. Okay, so if you want, you can represent it as alpha nm. If you want to remember that I first write n and second write m, you can write this as alpha nm. Okay, so this n is related to this and this m is related to this. You can, this is just a notation. Okay, now we ask a question that what is the relation between alpha nm and alpha mn? It should be complex conjugate, because when you take, since phi n phi m prime is phi m. Okay, so what does that mean? That means this is equal to phi m prime phi n star. Okay, phi m prime phi n star. So from here you can see that if you are thinking this alpha nm as a matrix, because this is like a matrix element, right? So this alpha nm is like a matrix element. So this matrix is a unitary matrix. So what does that mean? That means what we are saying here is that change of basis is like a unitary transformation. Our unitary transformation is like a change of basis. You can always represent unitary transformation and change of basis in the same fashion. That means in time evolution, what is happening? At 0 time, we are having one basis. At time t, we have another basis. Like that. The basis is changing. Right? So, in some sense, if we want to understand in classical, so first I want you to understand the following. Unitary transformation So I'm just trying to use this a useful unitary transformation. I want you to understand this. Please visualize it as a rotation. This is strictly not a rotation. It's like a rotation. Since here you have a Hilbert space, but the rotation is in a 2-dimensional space or 3-dimensional space, for example. But this is a useful visualization. So unitary transformation is like rotation. If you understand this, then so we have, let's say, 2 dimensions, this x and this y. And let's say I have a vector which is r, and this is equal to x times I plus y times j, if I choose I and j as my basis. Okay, so this is, let's say, is my position at time, at some time t equal to 0, let's say. Now let's say after some time this vector is rotated. This vector is rotated by an angle some theta. Now what happens? This is my position at r at t, okay, which is different from xy, right? This is different from xy. So this will be some x prime I plus y prime j. Now you know x prime y prime you can obtain from xy by using this kind of a matrix. If theta is the angle, cos theta minus sin theta, cos theta to xy. This is just a 2-dimensional rotation matrix. So my state has changed and components are changed because it is a vector is rotated. Now this vector is a different components. Earlier this was my x component, now this is my x component. So this was my x and only this is my x prime, correct? So the components are changing. Okay, so this is what actually happens in Schrodinger picture. As far as this analogy is concerned, the Schrodinger picture is rotating this vector. So this is actually called active transformation. In rotations in 3-dimensional space, we have something called active transformation. Active transformation is the one where we rotate the vector. But I could have also looked at it in the following fashion. So let's say I have a vector like this, r, which is equal to xi plus yj. But I can say that instead of rotating this vector by theta, I can imagine that I have rotated this axis. Okay, so let us say this is the theta. Now this vector will also be different because it is x times I prime plus y times j prime. And this is your x prime axis and this is your y prime axis. I prime and j prime are different, right? So whatever is your x here, so x prime, I prime, y prime, j prime. So whatever, this is your x. But then this will be your x prime. The components are changing because now the axis is changing. I can get the same effect of rotating the vector by rotating the axis. That means what? Now I have changed from basis. So the basis I comma j is changed to a new basis, which is now called I prime comma j prime. So what actually we have done here is that vector is not rotated. Vector is not rotated, but coordinate system is rotated. That means the basis is changed. Okay, and this is what we call as, this is what happens in Heisenberg picture. So since at every time the operator is changing, its eigenvectors are changing. That means the basis is changing. So this is what we call as passive transformation. So it is one easy way to understand that a Schrodinger picture is like a vector rotating a vector, and Heisenberg picture is like rotating a coordinate system, because here the basis is changing, eigenvectors are changing every time the operator is changing with time. Okay, so this is something which is the answer to this question, that what happens to the eigenvectors and what is the and what is the meaning of changing of these eigenvectors. Okay, so now let me just come back to the last part, that I have made an assumption that so that initial assumption that H is independent of time. Now let us relax that. Now we can have two cases. Case 1, H depends on time, but H at any two different times, t comma H at t prime, commutes. This is a simpler time dependence. That means, so just to give you an example, let's say I have a spin half particle, spin half system in a magnetic field, where magnetic field is given by B is equal to B naught of t, but in the direction of z. Okay, this is time dependent, but direction is fixed. So then what happens here? Hamiltonian is minus magnetic moment dot B, right? So that is your magnetic moment, and magnetic moment is equal to E by m. Okay, so E by m into S, the spin, right? So that is equal to electron, so let us say minus E, so that is equal to E B naught of t by m into Sz. So that is what is your magnetic field. So it is time dependent because B naught of t is time dependent, but then the only operator here is Sz, and at every time this coefficient is changing, but Sz is always commuting with Sz. So this is what happens in that. So if it is like that, then your psi of t can be written as e to the power minus I by h cross, and 0 to t h prime of h of t prime dt into t. You have to integrate this, and then you have this kind of a situation. Okay, so that is what, so you have to integrate, because it is time dependent. You have to integrate this and then do this. But then there is a more complicated case 2, where h of t is also not commuting with itself at different times. Okay, that means your h of t and h of t prime is not equal to 0. So just to give you an example of this, same spin half particle, but let's say this time the B field is such that it is B naught into cos omega t into I cap plus sin omega t into j cap. That means this, so it is like the magnetic field, if this is xy plane, the magnetic field is actually from x to y, it is rotating like this. So that means because of this, for example, when omega t is equal to 0, it is sx, and omega t is equal to pi by 2, it is sy, and sy and sx don't commute. So this is what happens in that case. Okay, and it's little complicated, but then I don't want to go into details. This is what you do in time-dependent problems using some time-dependent perturbation theory. But here also one can formally write, we can write, I'm not going to write it, but just give you the name, right? What is called a Dyson series. It's an infinite series expansion to represent this time development. But what I'm saying is, in either these cases, the unitary character of time evolution does not change. Only that you will not be able to write down that unitary operator in a nice fashion. It may be an infinite series and things like that, but that the time evolution is unitary is true either if it is in case 1 or case 2, or even if the time independent Hamiltonian. Okay, so since most of our discussion today is depending on the unitarity character, that is not going to change even if it is so. Formally, this entire discussion is true even if it is time dependent, but there will be only practical difficulties of implementing the unitary transformation. And that is where we have to do perturbation theory. Okay, so this is all I have to say about what I wanted to say. So I will stop here. If you have a question or a comment, you're most welcome.
Navya, can you read out the questions which is already posted in the chat box?
Yes, ma'am. So can I?
Yeah, please.
Stationary states are eigenstates of Hamiltonian. This it means the hydrogen atom is exactly solvable at an energy of minus 13.6 eV.
Yeah, so not only at minus 13.6 eV, there are all the infinite energy levels you will be able to exactly solve for hydrogen atom, right? So hydrogen atom has got all the energy levels, exact expression for both wave function as well as the energy eigenvalues. So for hydrogen atom, there is no problem. Everything can be exactly solved. Minus 13.6 electron volt is, it happens to be the ground state. But all other excited states also, we know stationary state eigenfunctions, we know stationary state energies. And that is the hydrogen atom problem that you study in your MSc.
Thank you, sir. If there is any queries, you can ask, please. Please feel free to ask.
Dr. Dyson wanted to ask.
Yes, sir has raised his hand.
Yeah. Yeah, Dr. Dyson, please go ahead. Is he there?
Dyson, sir. Okay, others, please carry on.
Myself, Manu KM from Sri Krishna College. I am a faculty in Sri Krishna College. I have one doubt. That means we have taken magnetic field as a vector quantity, not an operator. Why it is not an operator?
See, magnetic field is basically magnetic field, electric field, these quantities will have operators only when they are related to position and momentum, right? Otherwise, they are just time and magnetic field. They are only parameters. So if it has a vector thing, only saying that there are two different directions in which it can be there, but the field as such is not an operator.
Okay, sir. Okay.
Devika.
Sir, can I ask you a question?
Yeah, please.
Sir, I am Abhay from Marvinus College. So I'm studying my post-graduation MSc. So, sir, we have discussed about matrix representation, and so we will be obtaining a diagonal matrix only if when we represent an operator in its own eigenvectors, right, sir?
Correct.
So only we will obtain diagonal matrix in that cases only.
Correct.
So when we are solving a problem, if you obtain a diagonal matrix, that means that the corresponding eigenvectors are its eigenvectors. The corresponding vectors are its eigenvectors, right, sir?
Yeah. So when you do a similarity transformation, the columns of the similarity transformation must be eigenvectors of the matrix in order to diagonalize that.
Okay, sir. And sir, one more doubt, like suppose I have an operator A, and after a certain time it gets evolved. It becomes A of t. So we have discussed that the eigenvalues remain the same, but the eigenvectors changes.
Correct.
So since this Cn, the coefficient, their modulus gives the probability to find each of these eigenvalues. So for different times, does that probability also changes to find the same eigenvalue?
Yeah. Probability will change.
Oh, okay, sir.
Probability will change, matrix elements will change, but the eigenvalues will not change.
So for two different times, even if we measure the same operator, we will be getting different eigenvalues, right?
Correct.
Okay, sir.
That is also true in Schrodinger picture, because your state is changing. See, you have psi of t, and psi of t is different at different times, right?
Yes,
so
sir.
you take an inner product with the same eigenstate, you will get different values.
Yes, sir.
Yeah, so there was some other. Any other? I think there were another hands, but I did not remember. Swati. Oh, left the meeting.
Sir, I have one more question.
Yeah, please.
Most of the time-dependent problems, we use Dirac picture for solving the for finding the approximate solutions. So, is there some situations where we can use Heisenberg picture for these problems which do not have exact solutions?
See, the point here is that if the Hamiltonian, whatever I discussed, the formalism of both Schrodinger and Heisenberg picture today is a case where Hamiltonian does not depend on time, right? So if Hamiltonian depends on time, it has explicit dependence on time, then the interaction picture or Dirac picture is more convenient, because there the time evolution is shared by both operators and the state. Okay, so we didn't discuss that today, but interaction picture will evolve, states evolve according to the interaction Hamiltonian, which is time dependent, and operators evolve according to time independent. That is like Heisenberg picture, time independent part of the Hamiltonian. So it is mathematically convenient, and hence a time dependent perturbation is equivalent to doing an interaction picture. So that is convenient. Okay, so but if you want to do that in Heisenberg picture, it is possible to do, but only thing is some of those equations cannot be solved. You may have to solve them on a computer and things like that. Formalism is equivalent. Only thing is practical difficulties will be there.
Okay, sir. Thank you.
Yeah. Okay, any other questions or any comments? Or Dr. Dyson is not able to speak. Okay, so I'm not really sure if I have covered what is required. So I tried to do some justice to the given topic. Okay, so if there are no questions, then
So we hope there is no more queries. So can we wind up, sir?
yeah, okay, thank you.
Navya, I have posted the feedback link, so I request all the participants to fill in the feedback.
Rosalina, are you there?
Yes, sir. Yes.
Yeah. So if possible, you can share the link of this recording to me.
Yes, sir. Sure.
Thank you.
Okay, Navya, continue.
So I just invite Bini for vote of thanks. Bini, please.
Bini, you there in the meeting?
Yes, ma'am, we can hear. Yes, Bini, you can continue.
What happened, Navya?
Rosalina, can I say something?
Yeah, sure.
Hello, sir. My name is Geetu Amar. I am from St. Joseph's College. I come from a literature background, actually. But I found the topic very interesting. That's why I entered this lecture. And I thought that maybe I'll get bored initially and would leave the meeting because it's all about all those equations that you learn in physics. But then the energy of the class was so calming, and I thought I'll stay the whole session. So while you are exploring beyond your discipline and thinking about some fundamental laws of the universe and things like that, such things in physics also come up into our realm. So thank you very much for this class, and I think it was very beneficial for me.
Thank you. I think it is the greatness of the field that it has captured you. That you are able to sit and listen 2 hours of quantum mechanics, even you are coming from literature.
Yes.
I think credit goes to quantum mechanics.
Thank you, sir.
Yes, Bini, you are audible.
I think Bini is not audible.
No, it is audible. It is audible.
Okay, all the participants kindly turn on your video so that we can take a snap. Am I audible?
Yes,
Yeah,
yes.
yeah.
Yeah, please, all of you, please turn on the video. I hope all of you have completed filling the feedback form. Thank you once again for joining the webinar. Thank you, Satya sir.
Yeah, thank you. Thank you very much.
Hope to meet you in future.
Yeah, sure.
Once more, thanks to all the participants for your interest in joining the webinar. Thank you.
Okay, bye-bye. All the best.
Thank you, sir.
Thank you, sir.
Thank you, sir.